So, radiometric dating. And it's specifically, we're going to talk about carbon-14. So, radio, you can probably figure out, has to do with radioactive. And the suffix here, in this case, metric, has to do with measurement. So, radiometric dating is finding the age of something based on its radioactivity. For living things, I should say, carbon-14 is a very useful isotope to use. Remember, carbon maybe I'll do this right now. So remember that, I'm hoping that's what's going to record. We'll find out. So carbon-14 is one form of carbon. What's the most common isotope of carbon? Anybody guess? Look at its place on the periodic table. It is element 6, so whether you're carbon-14 or you're this other one, you're element 6. So remember, carbon, what's this number say right there? You guys read it? 12.0011. Okay, so what's the most common isotope of carbon? 12. Good. So this is most of the carbon in the universe. There's a really tiny, tiny bit of this carbon. Carbon-14 is radioactive. So we sometimes note that with a little asterisk. Okay. So here's my questions for you. What's the 6th part? Gotta know this. Protons, exactly. What's the name of the number of protons? Yes. Atomic number is the number of protons, and that's how we arrange the elements on the periodic table. What's different about these two carbons is this number. What's the big number tell us? Mass number, and it's different isotopes. What does the mass number tell us? Number of what?
Neutrons and protons.
Good job. Neutrons and protons added together. So we know that carbon-12 has 6 neutrons, 6 protons. Carbon-14 has 6 protons, but it has 14 minus 6, 8 neutrons. And that makes it unstable, aka radioactive. Okay? All right. So we did that. Some other things I want to go over before I switch back to the PowerPoint. A lot of people were having trouble coming up with what I wanted. There was a table I asked you to fill in on one of them on particles. So 3 types of radiation: alpha, beta, gamma. Alpha particles are helium nuclei. There are 2 protons and 2 neutrons. 2 protons is the same as the element helium. 2 and 2 is 4. So when we write an alpha particle in a decay equation or capture equation, we write it like this. Keep track of the mass number and the atomic number. Beta particles are speed electrons. Which again is really bizarre. How can you have an electron in the nucleus? You're not supposed to, but whatever. It's how it is. So again, some books use the beta. I prefer that you use this. Little e for little tiny electrons. Negative because the beta particle happens when a neutron turns into a proton. I forgot to do proton with you guys. Okay, and then gamma is just radiation rays. And so we just write the little loopy bottom loop like a bottom OG. You can use 0, 0 if you want. You don't have to. That's wasted pencil lead as far as I'm concerned. Okay? So just a loop and you're good. So again, I've already alluded to two other particles. A neutron is lowercase n. It's not a proton, but it is a neutron. So this is how we use it in the tables. A proton. The element with one proton is hydrogen, and actually the most common form of the element hydrogen is protium. One proton, no neutrons, one electron. Okay, and then the last one is, and so remember, protons are positive, neutrons are neutral, electrons are negative, beta particles are negative. There's one more particle that's positive. You guys remember? Yes, nicely done. So a positron is the antimatter equal and opposite of a beta particle. So it looks like the same notation, slightly different. It's +1 instead of -1. This is good because I'm hoping on Friday, I'm sure every other teacher might be also, but Friday's the end of the second quarter progress report period. And it is before a week off. So I'm thinking we do an assessment on Friday, but we'll see what transpires this week. All right, questions on any of that? So a good review? You guys good? Does it make sense? Do you remember all of it? No, sort of. Okay. All right, so I'm going to just leave that up there. Okay, so I'm going to switch back to my PowerPoint. Okay, let's talk about carbon-14. So carbon-14 is a radioactive isotope of carbon, and it can be used to age date things that used to be alive. It's kind of cool. It was first used extensively by a gentleman named, I can't remember his first name, Libby, L-I-B-B-Y, you don't have to remember that. In 1947, he started using carbon-14 to age date known artifacts. So, for example, you guys know Mount Vesuvius erupted in Italy, and the city of Pompeii got buried in ash. You guys might have seen some of those pictures before. So that is known in time when Pompeii got buried. Right? It was recorded history at the time, around 79 AD. And so we have record of that. It's a known event. And there are things like people and dogs and all sorts of things buried in there, and they have castings of their bodies. But they also had a loaf of bread from that time that was covered with ash and encapsulated for a couple thousand years. Well, he tested it with carbon dating, and voila, it came out at the right time.
So it didn't
incinerate. No, because it got buried. So much ash came out of that the ash actually probably smothered everybody to death. But anyway.
So it didn't just turn into
It might have been toasted. I don't know. That's a good question. Ugh. It's so sad to see those pictures. Have you guys ever seen those pictures?
Yeah.
Oh, there's like a mom over a baby. And I was like, oh. Anyway, okay. That was history. So, and then he also did some stuff on boats from pharaohs, known aged funerary boats for some pharaohs, a shroud that was around with the mummy they believe is Cleopatra, all that kind of stuff. And ashes from fires at Stonehenge. I mean, all sorts of crazy stuff. Anyway, all of them dated beautifully with carbon-14. He ended up getting a Nobel Prize for his work with that in 1960. He also, using this process, they also did some other things like the Shroud of Turin, which used to be a very, well, it still is a holy relic, but it used to be believed that it was the wrapping of Jesus in the tomb. There's like an image of a person on it. It's not, it's only about 500 to 600, a lot of the time, I think 600 to 700 years old. So that's not old enough to have been in Jesus' tomb, but it was used also to verify the age of the Dead Sea Scrolls. They were found in some pottery jars and a cliff near the Mediterranean somewhere. And indeed, they were dated to be about 2,000 years old. So there's some interesting things that they've used carbon-14 for. All that being said, so here is a diagram, and this is not from our textbook, it's from a different textbook, but it shows kind of the process. So where radioactive carbon comes from starts with the sun. Cosmic rays are constantly being shot out from the sun. And cosmic rays are mostly protons. So the sun is mostly hydrogen and some helium. And so element 1, helium, right, and helium. And so stuff's being blasted off. We call it solar winds. Also, it's being deflected by our magnetic shield, our magnetosphere. But some of it gets in through the atmosphere, runs into atoms. When a cosmic ray runs into the main gap, well, oops, I got to go back a step. Sorry, I forgot one step. Let me go back. One of the things probably, I hope most of you know, 78% of our atmosphere is nitrogen gas. Lightning rips nitrogen gas apart into 2 nitrogen atoms. Okay. Then come cosmic rays, and then they slam into that nitrogen, a nitrogen. And that ends up causing the nitrogen to poop out a proton. How's that for high-tech science? Okay. So a proton goes out, high-speed neutron comes in, a proton comes out, and we end up with one less proton, one. So remember, let me go back here. So nitrogen is element 7. Most common form of nitrogen is 14. What does that mean? It means it has 7 protons and 7 neutrons. If a proton comes out and a neutron goes in, you're not nitrogen anymore, you're carbon-14, and that's radioactive. So that process happens in the atmosphere. That carbon doesn't just hang out in the atmosphere, it gets attached to oxygen. And of course, carbon with 2 oxygens makes carbon dioxide. Okay. That's radioactive. And you guys know, of course, because you're good biology students, plants are dioxide and photosynthesis. So plants are using that CO2 to grow. It's radioactive. It's just a little bit. It's not the end of the world, right? Everything's radioactive. We have to understand that. So the plants take it in. The plants become radioactive. You and I eat plants and animals that ate plants. That's what makes us radioactive. When you stop eating or stopping as a plant, you're dead. And so then you stop taking in radioactive carbon. And then eventually that carbon-14 will decay back to nitrogen through beta decay. Okay? So the radioactive carbon comes in from the atmosphere into plants. Plants are radioactive. You become radioactive because you eat plants. When the plant dies or a plant stops living or you stop eating, you stop taking in radioactive carbon. And slowly that radioactive carbon converts to nitrogen. Right? One half-life, you have 100%. Right at the time of cutting down the tree, it's 100%. One half-life later, it's half of that, half of a half, half of a half of a half. Okay? And that's how you can age it. Now, it doesn't have to be a full half-life gone to be able to measure it, right? 5,000 years? Hello? You know, we haven't been doing recorded history for that long. So this is percentages to make it easy to conceptualize. But we can, 50% is to this much as 75% is to something else, right? You can do proportions and calculate how much radioactive or how old something is by how much radioactive carbon it still has. Okay? And that's how carbon dating works. So I need to do carbon dating on a relative, but you probably shouldn't say that to your grandpa. Ha ha ha! So this curve is classic probability curve. You've seen it before. 100%, in this case 1 gram. At the beginning, after one half-life, there's half of it, half a gram. After 2 half-lives, there's 0.25 grams, et cetera, et cetera. Most radioactive dating of any kind, whether it's carbon or some other isotope, they say 6 or 7 half-lives max. By the time you get out here, out at 9, 8, 9 half-lives, and this is also held true with our Skittles, right? Most of you didn't have any Skittles left after 8 half-lives. Okay, 30,000 years is about the maximum for using carbon-14 for aging artifacts. And again, there are other isotopes. So uranium-238 is the isotope that we use to measure the age of the Earth. 4.5 billion years is the half-life for uranium-238. And you should go, well, wait a second. Humans haven't been here for 4.5 billion years. You're right.
The Earth was here before humans.
That's correct. And so we can't know exactly we know how rapidly uranium-238 decays. And they do calculations from that little tiny amount to backtrack it to the half-life. We'll do some of that Wednesday or Thursday. All right. The other topic today is transmutation. I think we'll get this done. Transmutation. So trans has to do with changing. Mutate also has to do with changing. Transmutation is what the alchemists wanted to do. We want to change one element that's not valuable into another element that is. Lead into gold, iron into silver, whatever it might be. So what's the definition? Conversion of an atom of one element into an atom of another element. You're changing one thing into something new. Okay? You start with something and you end with something else. 2 ways that can happen. You can do decay or emission. Okay. 2 words that mean the same thing. Or a particle can be captured. So we went through the particles. Okay. We went through what they were. If I say alpha capture, the alpha particle is going to be to the left of the arrow. If I say beta decay, the beta particle is going to be on the right of the arrow, for example. Okay, so it tells you where to place whatever particle is mentioned, and then you do the math from there. So carbon-14 does beta decay. Write the equation for the beta decay of carbon-14. What are we starting with? Carbon-14. If you don't know the atomic number, it's fine. Look it up on the periodic table, okay? Beta decay, beta particle over here. Now it's up to you to figure out what's left. =14 0 plus 6 equals -1 plus. What's going to happen in this process? Everybody write it down. See if you get the same thing I do. You guys get nitrogen 14? Okay. So that's how you do beta decay. All right, I'm going to switch off this microphone and go back to my. All right. So let's look at this one more example. So example of a capture is this one. So the very first transmutation, artificial transmutation, not spontaneous. So all the stuff we've been talking about so far is spontaneous. It happens by itself. This is man-made transmutation, was when alpha particles are being shot at nitrogen atoms. So this should sound familiar. Who was shooting alpha particles at the gold foil? You guys remember? Ernest. Rutherford. Okay, so he's shooting alpha particles at nitrogen. Okay, so what am I going to get if I do that? Doesn't even matter what they are. 4, 2. If this alpha particle is going at the right speed, hits at the right angle, everything goes perfectly, we stick together. What are you going to get up here? 4 and 14. Good go. 2 and 7. Good. What element is 9? Fluorine. Yep. And guess what? This fluorine is radioactive. So for a very brief time, he made fluorine gas, and then it very rapidly decayed into oxygen 17, and a proton was released. So that is our friend Ernest Rutherford. And so he's the first guy, you know, he tagged them alpha and beta, and he did all this shooting at things with his alpha particles. Since then, we've been building lots of new elements. Every element after uranium is what we call trans-uranium. It's after uranium. Uranium is element 92. So anything from 93 to 118, only made in the laboratory. It's not real, or not on planet Earth naturally. Another element, technetium-43, is also only found in nuclear reactors, polonium nuclear reactors. It's actually used a lot in medicine, and when the reactors have to go down for repairs, it's kind of, there was one period there for about 2 years, there was a shortage of technetium, but anyway, another story for another day. Okay, none of these occur naturally. Again, Uranus is a planet, Neptune was the next planet, Pluto used to be a planet, and Americium, Curium, Berkelium, Californium, Einsteinium, Fermium, about half a dozen of those were first made at Berkeley and what lab is now Lawrence Livermore. Okay, this is a picture inside a linear accelerator. This looks a lot like the one at Stanford, but I think this was at Fermilab. I've been in the one at Stanford. This is Fermilab. It's outside of Chicago, and it has a linear portion. You can tell above ground the tracks here. It's underground, however, I believe. And then there's 2 cyclotrons, 2 circular speeder upper rings. So they're pulse electricity and magnets to make the particles, give them a little push around until they get up to almost the speed of light. And then they, they're going around in separate rings, and then they turn them so that they collide. And that causes an event in the detector. This is an image from, looks like it's from Highway 280 over by Stanford. A lot of you have been to Stanford for their track meets and stuff. SLAC, Stanford Linear Accelerator. It's very visible. I think this is a 2-mile run right here for the particle accelerator, and the event and stuff happens here. We used to be able to tour that. You can still tour it. It's not active anymore. It's an atom smasher. And then this is the big baby that is doing all the research right now. This is CERN, and it's something in French. It's at the French-Swiss border. This is 17 miles in circumference. It is 300 meters below ground, deep below ground. It's 3 stories tall. Inside, they made a tunnel 300 meters tall. This is a guy in here in the facility. It's been working. There were people that thought when they fired this puppy up in 2010 or 2009, whatever it was, we're going to create a black hole on Earth. That didn't happen. But there's lots of different little sub stations here. So it's called the Large Hadron Collider. There's Atlas, there's Alice. There's all these other little names for places. Huge international joint effort to figure out what stuff is made of. Okay, physicists from 130 countries, I think. We were going to build one here in Texas in the 80s. They started talking about it, and people said it was too much money. So we jumped in with the rest of the global community and helped build this. What happens is a particle smash together, and just like a car crash, pieces go everywhere. And those pieces, depending on their charge, will go to different directions. Negatives go to positive, positive go to negative. Little particles for the same size smack go farther. Big particles don't go as far. There's all sorts of particles known, named, described, cataloged. This 4-minute video or 5-minute video I'll put up for you. I may play it at the beginning. First period is the only one that got to see it. I may play it tomorrow because it's really a good introduction. So that's from 2010. And then in 2012, we did find the Higgs boson. They did verify that, and no black hole. So questions? That was a lot of information. Questions? Okay, so what the plan is then, my darlings, is tomorrow we'll talk about the lab and look at graphing the lab. And yeah, that's the plan.